Okay, I want to look at one more example for the ANCOVA procedure. And if we turn a little further into lesson 27, all the way over to page 221, exercise 1. And if you call that data up, or call that up, and it'll look like what I think is on your screen right now. And the scenario is, I'll just try to paraphrase this kind of quickly. We're looking at what kind of professors you think might be able to fix cars. And we've got a couple different groups. We got several things we're measuring. We're going to have to decide how to handle this. So, as it says, Sam is interested in the relationship between college professors' academic discipline. That's the independent variable. That's the group. And if we look at the group variables, and I go over to data view, I'm going to see that 1 represents professors from mechanical engineering, 2 is psychology, and 3 is philosophy professors. Gee, I wonder which one would be able to fix cars more. But anyway, those are the ones that we're testing. So that's what group means. And the kinds of things that we can fix on cars are these things. Let's see. Changing the oil, changing the points and plugs. Cars don't have points anymore, but they tell us that we're working on a 1985 Pontiac. I guess 85 Pontiacs had points. Now everything's electronic. That doesn't mean anything to you, probably, but that's okay. Change the points and plugs. Adjusting the carburetor, something else cars have no longer. Pretty much everything's fuel injected in the carburetor. And setting the timing. So changing oil, changing points, adjusting carburetor, setting timing, things that you used to know, somebody used to have to be able to do when you drove cars, or you had to know somebody who could do that. So, and I also have a measure of mechanical aptitude. And I'm told that the mechanical aptitude score is on the mean is 100 and standard deviation is 15. Sounds a lot like the old Stanford Binet IQ test. Very close to the same numbers. And these scores under the things that you can fix on cars, they have to do with times, how long it takes you. So low score is actually better. Kind of like that day sick example. The lower the number was, the better you were. So the problem I have, the first thing I have to deal with, is that I don't have a single measurement of being able to fix cars. I've got measurements of changing the oil, changing the points, adjusting the carburetor, adjusting the timing. So what I'm going to need to do is I'm going to have to put these together into one measurement. And I like when examples make us do this sort of thing, because this is a useful thing to be able to do with SPSS when you have real data and you're doing real work. What I'm going to do is I'm going to calculate just an average of all these things. And that's going to be my overall score to be able to measure how they can complete automotive tasks. So I'm going to go to transform. Now, we've done this a couple other times before. This has nothing to do with the covariate stuff, but it has to do with the other real stuff you're going to encounter. So I'm going to compute variable, and I'm going to call this, what do you want to call our overall ability to fix cars? Something creative like fixability. I just made that up. I don't care what you call it. So we're going to take into consideration those 4 things that are fixed, or the degree to which they can do those 4 things. And I think I just want to take an average. How do you take an average? How do you average something? Oh, gee, this is back at day 1 on the previous course. Actually, before that, because you already knew that already. So to take an average, you add them all up, divide by how many you have, right? So what I'm going to do is I'm going to add them all up. I'm going to open up some parentheses. And inside that parentheses, I'm going to take the changing oil scores, add to that with just simply the plus key. The changing the points score, add to that with the plus key. Adjusting the carburetor score, add to that with the plus key. Setting the timing score. And that'll give me the sum of all those things. And I could use that as my score if I wanted to. But the reason I like to take the average is because of this. If you're giving a score from, say, something that has a Likert scale, say a 1 to 5 Likert scale, and if you take the average of all those numbers they've circled, then your average is going to also be on a 1 to 5 scale. So you're not going to change the scale. So I'm going to take that sum, and I'm going to divide by, and the slash is the divide sign, I'm going to divide by 4. Add all 4 things together, divide by 4, that's my average fixability score. And again, keep in mind lower is better because it has to do with how long you take. So when I click OK, I'm going to get an additional column headed by the word fixability, just because that's the name I picked out. So I click OK, and I get my output window out of the way because I know what it did. Doesn't have to tell me. Don't want to save it. And there are my fixability scores. So person 1 had a fixability score of 85. Person 2 had a fixability score of 84.75, which is slightly better, but again, because lower is better. So my independent variable is the group. My fixability score is the dependent variable. My covariate is the mechanical aptitude score. So to run an analysis of covariance, first thing I need to do is to see if I can run an analysis of covariance. So we're going to start with Analyze. Go down to General Linear Model, and it's univariate because there's only one dependent variable. And there's room for only one dependent variable because I told it univariate. So fixability is the dependent variable. The professor type is the fixed factor, or the independent variable. And my covariant is mechanical aptitude. Don't you suspect between philosophy professors, psychology professors, and mechanical engineering professors there might be some difference to begin with in their mechanical aptitude? I'm hoping so, or we're not getting our money's worth for the mechanical engineers. So the mechanical aptitude is the covariant. So I've got everything in the right place. I'm going to then go to Options. I'm going to move the independent variable over. There's the only thing that says there, Group. And I'm going to select Descriptive Statistics because I want means and standard deviations. Estimates of effect size because I want the eta squared. And Homogeneity test because I want to see if it's too far out of whack to conduct the ANCOVA. Going to go to Continue. Going to go to Model. Going to select Custom. And then I'm going to move everything over, not just individually, one at a time, but then also both at the same time. And you can hold down the Shift or I think the Control key for that will work too. So I want that group by mechanical aptitude line to go over. Again, I don't know why it doesn't just give us that as an option, but it doesn't. So because it did with another procedure. Okay, kind of caught up. We continue, and we click OK, and that's going to give us an output window. And there's my output window. And the part of that output window I want to see is on the test of between subject effects, the part where it says both of them together, the group by mechanical aptitude. And the key thing I want to look at is the p-value. So does this tell me I can go on or I can't go on? It's not significant. And keep in mind what we're testing to see whether it's significant or not is, are the initial differences too great to do the ANCOVA, too great to adjust for? And they're not, because it's not significant. So the differences are not too great to adjust for. Therefore, we can go on and perform the ANCOVA. Somewhere that I want to write down something like f of 2 and 9 equals 3.085. The mean square, MSE, is 2.327, and my p-value is 0.095. And also there's my eta squared, if I need that. So far that tells me I can conduct the analysis of covariance. So if so, I want to go back to where we're going to analyze general linear model and univariate. And again, things will be the same place I left them. It's not going to move anything. You know, the little ANCOVA fairies aren't going to go rearrange things on us. So I see everything we've left. But I need to go back and undo a couple things, or go back and redo a couple things. One is that I want to go back to model, and I want to go back from custom to full factorial. And then I want to continue and go to options, and I want to select compare main effects. So in the write-up, the first half of the first paragraph would be what we just looked at, the homogeneity of slopes test. The second part of that, again, I would probably look at as a second paragraph, but if I go back and click continue and then finally OK, I'm going to get an output window to tell me that, there it is. Now I've tested between subject effects, looking at, again, group and error lines, the rows. I can see that F for 2 and 11 degrees of freedom has a value of 55.397. I'm not going to round off because it's easier to tell where I'm getting from if I don't round off. My mean square, there's my F value. My MSE is equal to 3.208. My p-value, again, can't say 0, less than 0.001. Eta squared is 0.910. So that means 91% of the variance relates to the other part. Okay, because this is significant, I've got a third step to do. I've got to look at the pairwise comparisons. I've got to look at the three things in terms of two of them at a time. I've got to compare the psychologist to the psychology, whatever they were, to the mechanical engineers and whatever that other one is. Psychology, was it sociology? Yeah, find out. Oh, philosophy, that's what it was. Okay, so I'm going to compare mechanical engineers to psychologists, mechanical engineers to philosophers, and psychologists to philosophers. Is there any significant difference on those three lines I've marked? And the answer is yes, yes, and yes. They're all significantly different from each other. Now, which way, though? And here's the question I told you I'd get back to. So, yes, mechanical engineers are significantly different from both the other two. Everything's significantly different from everything. So they're all different. Let's go back up and look at those adjusted means again. There they are. I could have probably kept that on the same screen. Okay. So looking at these means, I can see that, again, keep in mind the lower score is the better one. So mechanical engineers have the lowest scores. Well, that's good. I want them to be better than the psychologists and philosophers. So mechanical engineers are clearly significantly higher than both the other two. And the psychologists are clearly lower than the mechanical engineers, but clearly higher than the philosophers. And the philosophers are clearly significantly lower than each of the other two. At least according to these data. So I would suggest that when you write up your APA example, I would suggest doing this example as a write-up. Because the homework problem I've given you is, I'll just tell you up front, that there's not going to be significance at the end. Not that that makes it better or worse, not that there's anything wrong with that, but if you can write up something where there's a significant difference, I know you can write up something where there's not a significant difference. If you really want to write up the other one, that's fine too, but I would suggest this. So no penalty if you don't choose that advice. So let's look at that. Any questions about this example before I want to talk a little bit about that homework problem. I'm not going to do it for you, but at least not yet. Okay. Let me get rid of this. Homework problem is exercise 2. Description is found at the bottom of page 221. And it's labeled in your Green and Salkin data stuff as, what I say, lesson 27, exercise file 2. What we're looking at is, this is an interesting one. Marilyn was interested in the effects of journal therapy on depression. Well, there's an uplifting example if I've ever seen one. So journal therapy is the independent variable. The depression score is the dependent variable. That's their depression score after they went through the therapy. But how do we know whether or not they were depressed at equal levels for both groups, or however many groups we have, before the treatment? And we don't, but we can adjust for that if there's adjustment to be made. So I'm looking at 1, 2, 3 different groups, and I've got depression prior to the therapy and depression after the therapy. So let me set us off on the right track. The group is the independent variable. The depression after is the dependent variable. And the depression prior is the covariate. If you don't get those in the right place, nothing works right. The group is independent. Depression after is dependent. And depression prior is covariate. So does that help you get started on that? And again, spoiler alert, you're not going to find, if my notes are right, if I did this right, and I did it recently too, there aren't significant findings at the end. So I just tell you, if you get that, you got something wrong. But you wouldn't get that. That's why I suggest you not write that up. Just a suggestion, not a cordial requirement or anything. There are not significant findings, no. So do I need to recap anything? Group independent, prior depression covariate, depression after dependent. Yep. The question is, do I want to see the output? I do not want to see the output because I know what that is. I want you to answer the question, do the analysis, and tell me where there's significance or not. That's the main thing here. So without giving away too much, there's a little bit of a hint. Okay, so we're good to go on this? Okay.